Alright, funny story, people. I just recorded a video doing what I'm about to do, but I actually forgot to press record. I can't even say it, like I'm so embarrassed. And it was beautiful, it was like poetry, but I forgot to press record. So here it is, take two. So we're talking about limits, and we gave you the context of Hermione and Krum getting closer and closer to one another, but due to social distancing norms now, 6 feet is the closest they can get. That's the limiting value in terms of the distance they can get to one another. But in terms of more in lines with math that we'll see it, here's another way to see it, that you'll see it on your on some of those Khan Academy videos. Here's some expression. What does this expression equal as x gets closer and closer to 1? If we let x equal 1, we get this 0 over 0, which is undefined, or anything divided by 0 is undefined. The universe blows up, so it doesn't work. We can't do that. But by limiting, and what that means is taking x closer and closer and closer to 1, we see what in this case the expression evaluates to. That tells us its limiting value. So as x gets closer and closer to 1, this expression gets closer and closer to 2. So when we talked about E in terms of the research that you're doing and the video we watched. Oh, and by the way, don't worry about the research on E right now. That's kind of put that on the side. Don't sweat it. Just we did watch the video, so let's just kind of use that as our context. And in it, James Grimes talked about how e to the x is so special because when you evaluate the function at some given x value, let's say 2, we get this number, and that number is the slope at that point and the area underneath that curve, which is amazingly cool. That's just cool. And you can imagine, you know how I talk, and so you can imagine me putting my fist in the air and like pump it in the air, hitting the air, going, that is amazing. And we're going to talk about limits and this e to the x function. So here, in terms of line, so as we bring this point here closer to where x is 2, we can kind of see that the slope of this red line is getting closer and closer and closer to the value given by the function. The actual value is 7.38, or the most approximate is 7.38 and change. Here it's 7.03. As we get closer and closer to x is 2, we see it's closer to that 7.389. So what I'm going to have you do is make this Desmos graph with me. I'm going to erase this and start again. And I want you to do it with me so that you can kind of get a better understanding about limits, secants, tangents, and this point slope formula line that we haven't talked about in a while. So I'm going to start fresh just like you are. There we go. So here's our number E that we were learning about. 2.718, 281, 828, 46, more and more. And if you want to do pi, you can start typing pi, and there it is. There's also a number called tau, T-A-U, which is 2 times pi. There you go. But anyway, E, we want f of x equal to e to the x. And then we need to get that point, or the value of the function at 2, so f of 2. If we want 3, we substitute 3 for x, 4, 5, and so on and so forth. But let's just stick with 2. And then we also need we want to see that point on the graph, so we need to write the point 2, comma, f of 2. There's the x value and the y value. X is 2 and the y is 7.389. And then we're going to work with the slope of a line between 2 points. This is the slope formula right here. And then previously, last semester, we manipulated this to get the point slope form of a line. In this case, y and x are your variables, and y1 and x1 are a specific coordinate, and then m is the slope of the line. Here's another visual of it. You can pause it to take a closer look at it. So we're going to use that. We're going to define our slope. We're going to define the slope. We need to give it some specific value. So we want m equals f of 2 minus, let's see, f of a divided by 2 minus a. Ignore it. You can just turn that off. Don't even worry about that function. Don't worry about that. Just ignore it. But we need to give it some a value. A equals 1. There we go. And now we can, as we change the a, this is the slope that we're going to use. But now we need the point slope form of a line. So based on our previous notes here, we have y minus a specified y value, f of a, because a is the thing we're changing. M, we're using this m value, this specific m value. And m times the quantity x minus a. And there we go. There it is. Pretty nifty. But so we can drag the point. Desmos needs you to define the point, so we're going to say a comma f of a. There we go. Now we have this point we can drag along our green e to the x curve. There we go. So what we have now, this is called a secant line. Let me spell that for you down here. S-E-C-A-N-T. Secant. Hang on, let me do that better. I'm going to add a note. That way it's not trying to write a formula. Secant line. And a secant line is a line that crosses a function at 2 or more points. But as we bring a closer and closer and closer to where x is 2, we're getting closer and closer to becoming a tangent line. Tangent line. And a tangent line is a line that touches a curve at only 1 point. So right now it's technically touching it too, but as we bring it closer and closer and closer, it's going to become a tangent line. But in terms of where it's equal to 2, we have a problem because we've now got 2 minus 2 in the denominator, which means we divide by 0, and that doesn't work. But the idea of limits is that it allows us to get something really close to what that value would be. And by sliding, it's hard to be accurate because but if we type in 1.99999, I keep adding some 9s, we'll see the slope is getting closer to the value of the function, which is also the slope at that point. There we go. Pretty cool. Pretty cool. And as you can see on our graph, it almost looks like they're on the same point, but if we keep zooming in, eventually they won't be. And what's cool about this setup is you can change this e to the x to be x, say, cubed, and we have the same, we can do the same thing where we drag our point around, Now it's a secant. Our black line is a secant line. As we bring a closer and closer to, in this case, 2, making it almost a tangent line, you can see the slope is getting closer to be almost 12, pretty close to 12 at that point. But now just to notice, where f, in this case, we've changed our function. That's not the slope that we're getting. So that's one of the reasons why e to the x is so special, is that it has that property, where the value of e to the x at a specified x value is its slope. That's pretty cool. So build this, practice with it, play around with it, save it. You can go to here, save it, make sure you're signed in. You can title it Super Amazing Quarantined Graph. Quarantined graph. There you go. And then it's there for you anytime you want to do this same kind of thing. All right. Be well, people. We'll talk soon. Toodles.